Hi class, so this is our last section in chapter 8. This is 8.8 and we're going to be discussing partial pressure of gases, which is commonly called Dalton's law. So our cells continuously use oxygen and produce carbon dioxide. So we have both gases moving in and out of our bodies, and they have, each of them, or all of the gases, have partial pressures to them. And that's what we're going to look at. So you may not understand that right now, but let's get into it so you can. One of the things I want to point out in this drawing, you see that there's a pressure for oxygen, there's a pressure for CO2, and you can see it's in various different parts of our body. But what we find is that when we combine the pressures, they still, we can figure out what the total pressure by adding all these pressures together. The partial pressure of a gas is the pressure that each gas in the mixture would exert if it were by itself in a container. So what this means is that if you look at this picture, helium exerts a pressure of 2.0 atm by itself. Argon exerts 4.0 atm by itself. But what they have found that even adding these gases together still exert the same pressure. They don't change or modify their behavior because another gas is there. They act like they are completely alone in the container. So by adding these together, the total pressure of both of these mixtures, the partial pressure of helium and the partial pressure of argon, still equals 6 atm from the 2 atm from the helium and 4 atm from argon. So this is what partial pressure is. It is pressure depends on the total number of gas molecules, not the type of particles. And the total pressure exerted in the mixture is the sum of all the partial pressures of the gases. So think of it this way. If we have a container and we have several gases in that container, we need to figure out what the partial pressure is of that gas and of the next gas and of the next gas, and then add them all together, and that will give us our total pressure for the whole container. And since each gas acts like it's completely alone in there, the pressures of what it is by itself and the pressure that's in the mixture are the same. That's what this picture is stating. Okay, so for example, STP, 1 mole of a pure gas in a volume of 22.4 liters will exert the same pressure as 1 mole of gas in a mixture in 22.4 liters. So the pressure does not change for gases. Don't read too much into this picture. It's giving you an example, but I actually don't think this is a really great example, so I'm not going to focus on this too much. Okay, so let's look at this instead. The air we breathe. When we breathe, the air that we have around us and that we need is 21% oxygen and 78% nitrogen, if you take a look over here. So nitrogen exerts a partial pressure of 594 millimeters mercury, and oxygen exerts a partial pressure of 160 millimeters mercury. Then there's about 1% of other gases in the environment, which all of this equals up to 100. There's water vapor, argon, CO2. There's so many other things in the air, and all of that equals the total air, which is 760 millimeters mercury, which is sea level, 1 atm, and that still equals 100. So all of these pressures of gas would still have the same pressure if they were not involved with these other gases around them. So this is the sum of all the partial pressures gives us our total pressure, which is what our atmospheric pressure is at sea level and so forth. So how do we solve this? These partial pressures may seem a little confusing. They're actually easy problems. They're not some of the things that we've encountered that may seem a little bit more confusing. So let's look at this problem. A scuba tank contains oxygen with a pressure of 0.45 atm and helium at 855 millimeters mercury. What is the total pressure in millimeters mercury in the tank? So what we're given is oxygen, but it's not in the same units, and then we're given the partial pressure for helium. So this answer, though, has to be in millimeters mercury. So there's two things. We need to set up the equation, because this equals this. Partial pressure of one gas, partial pressure of the second gas, and so forth. So how many gases you have to have a partial pressure, and then add them all up to get the total of the whole container. So if we go here, That's what we did. We take the partial pressure of oxygen and we're going to add it to the partial pressure of helium, and that will give us the total pressure in this tank. But the first thing we need to do, we need to convert. This has to be converted out of ATM and into millimeters mercury for the oxygen, which is done here because we know the conversion, 1 ATM equals 760 millimeters mercury, and that gives us 342 millimeters mercury. So now we can take this and substitute it in where the partial pressure is here, and we can take the value for helium and add these together. And we end up adding them together, and it gives us our total pressure that's in the tank. So these are not too bad. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atm. If the oxygen has a partial pressure of 1280 millimeters mercury, what is the partial pressure of the helium? So we are given the total pressure. Unlike this one where we were solving for the total, we're actually given the total in this problem, and we're given a partial pressure of one of the gases, which is oxygen. We need to know what the partial pressure is of helium. So we're going to set this problem up the same way we did, but we're given the partial pressure of oxygen and we're given the total. We need to solve for helium. But before we can do that, we actually have to convert again. So we convert the 8 ATM to millimeters mercury. So this gives us our total that will be substituted in this problem. So here's the problem up here, and we're going to substitute this in. Now we're going to rearrange the problem for the unknown, which is helium. So what this has done is that we want to leave positives. We don't want to leave large numbers negative. So we're going to leave this number that would be plugged in here, and we're going to subtract. We're going to remove this from this side and subtract it and bring it on this side. The amount that we have, the partial pressure for oxygen, leaving helium by itself. So that's what you see, the P total minus the P oxygen, partial pressure of oxygen, and we can solve for helium. So we plug everything in, and it gives us our values. I don't like the way they did this. This is 3 sig figs, this is 2 sig figs, but basically they're giving us a problem to pick out of here, and it would be C. So this answer would be C. This should be like this and not like this, because this is 2 sig figs and we've been using 3 sig figs as far as I can tell in this problem. So this is the correct answer. This actually is not. It's only 2 sig figs. And that's it. Here is an overview for chapter 8. Everything that we have covered in this chapter, and this chart hopefully helps you understand each section of it.